item in and of itself is so ridiculous that every
Okay, there's a chat here. Okay, okay, thank you. Thank you. Okay, so I guess I'm clear. Okay, so let's start our lecture. Okay, so I guess this will be our first topic for this subject. So let's try to talk about the origin of soil and grain size. No? Okay. So for the topic outline here, we have yeah, just I guess I have also discussed this in geology, in your geology subject, if you still have such subject. But let's just try to recall these topics as soils are basically coming from rocks. Okay, that's the origin of soils. Okay, so let's try to understand a little bit about the rock cycle and the origin of soil. Okay, and the rock forming minerals. Okay, the rock and the rock structures, soil particle size, some clay minerals, specific gravity, mechanical analysis of soil, particle size distribution curve, and the part shape. Okay. Now, uh, later on, these things can be used to determine the typical shear strength of a particular soil material. Okay, so it's that's why it's important to understand um, their basic characteristics. Okay, so in geotechnical engineering, what is most important for us in the analysis are the shear strength properties of your soil material. No? If you try to recall in your subject strength of materials, okay, there you have a topic on Moore's circle. Okay, so I think in strength of materials, you might not well appreciate yet what's the purpose or what's the use of the Moore circle. So that's basically used to determine the shear strength of a soil material. No? In this case, we normally consider the Moore column failure criteria. Okay, but this shear strength properties of any type of soil, okay, is dependent on the soil particle sizes, the clay minerals, even the particle shape can be of importance. Okay, for example, if you hold a rock, okay, or a pebble, for example, okay, um, a rounded material can have a different shear strength properties as compared to an angular soil material. No? Okay, so this is quite important to distinguish between these things. Okay, okay, so that's just some introduction. Okay, so soils are formed by weathering of rocks. Okay, so the physical properties of soil are dictated primarily by the minerals that constitute the soil particles and hence the rock from which it is derived. Okay? So we need to understand the formation of the various types of rocks, okay? The origins of which are the solidifications of the molten magma at the mantle of the earth, okay? As well as the formation of soil by mechanical and chemical weathering of rock. Okay, I guess you're also discussing this in geology. Okay, so when we talk of mechanical processes in rock, this is probably due to erosions, okay, by wind processes. Okay, when you talk of chemical weathering of rock, this is when you have dissolution processes such as in limestones, okay, for example, wherein you can create caves, for example. Okay, if you try to understand how caves are formed, are formed. They are basically because of the chemical weathering of karstic. We call it karstic limestones. Okay, especially there in Cebu, we have quite a number of karstic limestones. No? I'm not sure if you're familiar with the Kabangkalan sinkhole area. Okay, somewhere there in Kabangkalan, no? Just near Talamban campus. Okay, there was a failure that happened there before. Okay, so these are just examples of chemical weathering and physical, mechanical weathering processes. So we need to understand also the determination of the distribution of the particle sizes in a given soil mass, okay, as well as the composition of the clay minerals, which provides the plastic properties of a soil mass. No? Because later on, I think in the third lesson, we will be talking about soil classifications. Okay, and there's what you call as a low plasticity silt. Okay, and there's what we call as a high plasticity silt. Okay, which is also called as an elastic silt. And then there's also what we call as a low plasticity clay, which we call as a lean clay. And there's also what you call as a high plasticity clay, which we also call as a fat clay. Okay. Now, this plasticity is actually derived from the clay minerals by which these clay particles are being derived on. Okay. So we also need to understand the shape of various particles in a soil mass. Okay. So these things we will discuss one by one. Okay. So the mineral grains that form the solid phase, okay, of a soil aggregate, okay, are the product of rock weathering. Okay. The size of the individual grains varies, okay, over a wide range. Okay. So later on, we will see those range. Okay. Then many of the physical properties of soil are dictated by the size, the shape, and the chemical composition of the soil grains. So to better understand these factors, one must be familiar with the basic types of rock that form that form the Earth's crust. Okay, so the rock forming minerals and as well as the weathering process. Okay? So on the basis of their mode of origin, rocks can be divided into three basic types. Okay, we have the igneous rocks, okay, the sedimentary rocks, as well as the metamorphic rocks. Okay, so again, in geology, you will be discussing them also. No? But again, here we just need to state them again because soils, all the soils in the earth, all comes from rocks. Okay, that's how they originate. Okay, so we need to understand these rocks just a little bit. Now, talking about igneous rocks, okay, so igneous rocks are formed by the solidification of molten magma ejected from deep within the Earth's mantle. No? Okay. So after ejection by either fissure eruption or volcanic eruption, some of the molten magma cools on the surface of the Earth, which we refer to as the extrusive rocks. Okay, so if they solidify outside the surface of the Earth, we call them extrusive rocks. Okay? But sometimes magma ceases its mobility below the Earth's surface and cools to form intrusive rocks, which we also call them as plutonic rocks. Okay? Now, intrusive rocks formed in the past may be exposed at the surface as a result of the continuous process of erosion of the materials that once covered them. Okay? Now, the types of igneous rock formed by the cooling of magma depend on factors such as the composition of the magma and the rate of cooling associated with it. Okay. So I think what is important to note here is that there are two types of two types of igneous rocks, which we call as the extrusive rock and the intrusive rocks. Okay. So later on, I will be giving some examples of these rocks, and I will be telling you which of those rocks are commonly found based on my experience, okay? Which we normally encounter in construction, for example. Okay. So, yeah, just a bit of this rock cycle. Okay. So here in the rock cycle, we can see now the origin, no? Which is, if you can see my cursor, this now the magma. Okay. Yeah, that's the magma here. Okay. It's coming from within the Earth's core. Okay, then the magma, based on some certain behaviors, okay, then it will become an igneous rock. Okay, and then from an igneous rock, okay, we have now some transportation of the materials happening, some erosion happening, and some weathering processes that's happening in such a way that these igneous rocks will become sediments. No? They will be disintegrated into sediments. Okay. Now, from the sediments, give it time, no? Just give it time because of certain compaction, cementations, and crystallizations. These sediments will become a sedimentary rock, okay, which we now call a sedimentary rock. And then from the sedimentary rock, it will just give it time. Okay, it will have some overburden. Then it will undergo metamorphism. Okay, so then it will become, or it will be called a metamorphic rock. No? Okay, by layers of rock. Okay. Then because of extreme heat and pressure, then this metamorphic rock, okay, will try to melt, and then it will just go back to a magma. Okay. And then the cycle repeats itself. Okay. The rock cycle. So again, from magma to an igneous rock, okay, to sediments, to sedimentary rock, and to metamorphic rocks. But sometimes igneous rocks will become metamorphic rocks, and so on. No? There will be a shortcut in the process. Okay. Depending on um, the behavior that's happening within these rocks. Okay. Now, because of this rock cycle, this guy, Bowen, he created a sort of a reaction series, no? Okay, wherein he found out that uh, with respect to weathering processes, okay, and with respect to temperatures, some minerals, okay, will be formed, okay, because of these weathering processes, okay. Um, and then for example, we have a mineral called olivine. Okay, and then it has a lower resistance to weathering. And then as you go to a higher resistance to weathering, then yeah, the olivine, it will become an augite mineral. Okay, then it will become a hornblende mineral. Okay, then it will become a biotite mineral, no? Or we call it the black mica. Now, these minerals here are basically what you call the discontinuous ferromagnesian series, in such a way that they have the same chemical composition and the same crystalline structure. Okay? Now, there's also what we call as the continuous plagioclase feldspar series. Okay, from a calcium feldspar, okay, crystallization at a higher temperature. Then as you go down to crystallization at a lower temperature, um, the calcium feldspar will now become a sodium feldspar mineral. Okay, so you notice here that a with the continuous plagal case feldspar series, they have a different chemical composition, but they have the same crystalline structure. If you notice, they have feldspar here. Okay, I'm sorry, what's happening here? Uh, they have a calcium feldspar. Apologies for that. So they have a calcium feldspar and then sodium feldspar. No? Okay, so if you notice, between these two, they have the same crystalline structure. Okay, that's feldspar, but they have a different chemical composition. Okay, and that's calcium and sodium. Okay, then as you continue with the process or with the reaction series, the sodium feldspar will become potassium feldspar, no? Or it's also called orthoclase. Okay. Then from the orthoclase, okay, it will become a muscovite mineral, which is also called a white mica. Okay. And then have more reaction, then it will become quartz. Okay. Um, Now, in the case of sandy materials, for example, um, quartz is the most dominant mineral. Okay. Okay. So just some composition of the minerals. Okay. Shown in the Bowen's reaction series. Okay. So if you recall, again, we have here, okay, these minerals. Okay. So we have the olivine, the augite, okay, the hornblende, the biotite. Okay. Okay, you have here the calcium feldspar and the sodium feldspar, as well as the potassium feldspar and muscovite and the quartz. Okay, so just a bit of a review of our chemistry. Okay, so this olivine is made of a magnesium or okay iron. Okay, then you have a silica. Okay, and then you have the oxides. Okay, that's the composition of olivine. Then for the augite, that's composed of calcium, sodium, magnesium, okay, iron, aluminum, okay, and this silica oxide. Okay. Okay. Then for the hornblende, okay, so it's composed of calcium, sodium, magnesium, aluminum. Okay. Then I forgot this chemical. Okay. Then for the biotite, you have the magnesium, iron, okay, and this chemicals here, no? The aluminum silicates. Okay. Then you have here the calcium feldspar. Okay, that's first that's composed of calcium. Then you have the sodium that's composed of sodium. Okay, and then yeah, you have here the aluminum chemicals, no? And silica. Then for the orthoclase, okay, you have here the potassium, okay, chemicals. Then for muscovite, okay, so I guess by now you're already familiar with these chemicals here, as well as the quartz, no? Okay. Um, okay, so please take note of these chemicals because later on, when we go to the clay minerals, some of these chemicals here will be mentioned again with respect to their reactions, no? Within one another. Yeah. Okay, so here we just have some, we call this scanning electron micrograph or an SEM, okay, showing the basal cleavage of individual mica grains. Okay, so this is about 10 micrometers. No? Okay, so sometimes in practice we sometimes require the SEM, the scanning electron micrographs, just to clearly distinguish between clay minerals. Okay. because there are some clay minerals which are a bit problematic. No? We call them problematic soils with respect to construction. Okay? So here we also see the scanning electron micrograph, okay, SEM of a fractured surface of quartz, okay, showing glass-like fractures with no discrete planar surface. So this is how your soils will look like if you um, try to zoom in, huh? Okay, to zoom um, in their structure. Okay. Okay. So, with respect to igneous rocks, okay, so we have here some of the names of these igneous rocks. Okay, so we have here the granites, okay, rhyolites, gabbro, okay, basalt, diorite, andesites, cyanide, okay, and these other two rocks. Okay, now again, for igneous rocks, there are um, two major types. No? You have the intrusive rocks and the extrusive rocks. Okay? So for the intrusive rocks, the texture of the material is a bit coarse. Okay, whereas for the extrusive rocks, the texture of the material is a bit fine. Okay, so for granite and rhyolite, the abundant minerals, the quartz. Okay, so if you go back, we go back here. Okay. So for the granite and rhyolite, okay, the abundant minerals are the quartz, the sodium feldspar, and the potassium feldspar, while the less abundant minerals are the biotite, the muscovite, and the hornblende. Then, for the case of gabbro and basalt, okay, so the abundant minerals are the plagioclase, the pyroxenes, and the olivine. Then the less abundant minerals are the hornblende, biotite, and the magnetite. Yeah. Okay. Now, in the case of diorite and andesite, the abundant minerals are the plagioclase, the hornblende, and the hornblende. And then the less abundant minerals are the biotite, the pyroxenes, quartz usually absent. Okay. And then for these two rocks here, okay, the abundant minerals are potassium feldspar, whereas the less abundant minerals are the sodium feldspar, the biotite, and the hornblende. So for peridotite, okay, so it's an intrusive rock. Okay, so it's the abundant minerals are the olivine and the pyroxenes, while the less abundant minerals are the oxides of iron. Okay. So far, in my experience, the common rock materials no, that we normally encounter in construction are the granite, okay, are the granite, the gabbro, the basalts, and the um, diorites, as well as the andesites, no? Especially in geothermal sites. Okay, when we construct geothermal power plants, okay, normally these are in the mountains, in geothermal sites, in Sorsogon, in Negros, in Leyte, as well as in Kidapawan. Okay, if some of you are from these places, okay. During my when I was in the industry for 3 years, no, these were the places where I normally go to, okay, almost every month because I was visiting these geothermal sites, okay, assessing some slopes, okay, and these are normally the rocks that I normally encountered, okay, this one, okay, this especially these andesitic rocks, okay, which are prone to weathering processes, okay, and they cause landslides. No? Okay, so when they become fully weathered, okay, then they can cause landslides no? In these geothermal sites. It's a bit tricky. Okay. Now, talking about weathering, okay, weathering process. Now, weathering is the process of breaking down rocks by mechanical and chemical processes into smaller pieces. So, mechanical weathering may be caused by the expansion and contraction of rocks from the continuous gain and loss of heat, which results in ultimate disintegration. So large rocks are broken down into smaller pieces without any change in the chemical composition. Now, physical agents that help disintegrate rocks are such as these glacier ice, wind, the running water of streams and rivers, and as well as the ocean waves. Okay. Now, a weathering process changes solid rock masses into smaller fragments of various sizes that can range from large boulders to very small clay particles. So, uncemented aggregates of these small grains in various proportions form different types of soil. Okay? Now, for example, when we do geotechnical investigations in the field, normally, we have what you call as we call it a borehole log, okay, a borehole log. So per layer, so for example, let's say from 1 meter to 1.5 meters, we usually describe the material that is being recovered, recovered from the drilling operations. And then normally we describe them as either boulders or cobbles, okay, or sands, shales, clays, and gravels, for example. Okay. So we describe that per layer, per depth. So for example, if you have a 30-meter depth of borehole, okay, you drill on site during the geotechnical investigation, and then you do the sampling every 1.5 meters, then that means there will be about 20 samples. There will be 20 samples in a depth of 30 meters, wherein we will have to describe each sample, each material. Okay. So in the borehole log, you can probably see there, okay, we have seen here in this depth, boulders, the next cobbles, the next sand, silt, clay, then again boulders, and so on and so forth. Okay. And that will be the basis of your geotechnical analysis later on to give the bearing capacities or the pile capacities, for example. Okay. That is needed by the structural designer. Now going back, the clay minerals, okay, which are a product of chemical weathering of feldspars, ferromagnesians, and micas, give the plastic property to soils. Okay. Now there are three important clay minerals. In practice, normally we try to look for these minerals. Okay, we try to distinguish between kaolinite, elite, and montmorillonite clay minerals. Okay, uh, I, I think the most problematic of these clay minerals is when you have the montmorillonite clay mineral, because these are the clay minerals that usually gives the expansive nature of clays, okay, which we don't want in practice. Okay, normally if we have expansive clays, um, normally I recommend to do remove and replace. Okay, or if you don't have a choice, you cannot remove it or you cannot replace it on site because there is a problem of disposing it, where to place it, then you have the option of doing ground improvement. Okay, we do some ground improvement techniques. Okay, now in practice, there's a lot of ground improvement techniques to address this problematic source. Actually, there's a lot of problematic soils. Expansive clays is just one. Okay, there's also what you call as collapsible soils. There's also what we call as liquefiable soils. Okay. So it depends on the type of material and how they are being placed below the ground. Okay, whether they are placed above the groundwater level or if they are placed below the groundwater level. That's why in practice, when we do geotechnical investigations, we always try to measure the groundwater level as accurate as we can because the behaviors of soil above the groundwater level and below the groundwater level are very different. They are not the same. Okay? So that's why we address these problems um, differently. Okay. For example, when you have a liquefiable soil, usually that happens below the groundwater level. But when you have an expansive soil or a collapsible soil, usually that happens above the groundwater level. But we have many ground improvement techniques that will address such problems. Okay. Normally, these ground improvement techniques are discussed in the masteral degree program, for geotechnical engineering. Okay. So here I've just shown these figures. Now, by the way, before I forget, to just don't worry about the slides. If you have the textbook or the reference book on the principles of geotechnical engineering by Das, okay, all of these things are just taken from the book. So you don't have to worry about copying or having a copy the slides. No? Just read the book because there are many things in the book that I did not present here, which you can probably learn more by further do readings, okay, as well as probably in the seat works, okay, with my colleagues, okay, Engineer Seno, Engineer Villena, and Engineer um, Ledesma. Okay, they can probably discuss this further with you during the sequence. Okay. So my goal here is just to try to give you as much concept as I can. Okay, as much principles as I can, sharing with you also the experiences that I had in the field, but most probably I will just focus on the experience, the geotechnical learnings that we had when we designed and built the Cebu Cordova Bridge project. Because that's something you can probably, or that is a structure that you can probably visualize. No? Okay. Okay. So here we have an example of a mechanical erosion process and a mechanical weathering process um, uh, with an erosion due to ocean waves and wind. So the figure here on the left side is because of ocean waves, okay? And then here, the figure on the right is, an erosion caused by wind. Okay. Uh, if you look at this rock, it looks like a person. It's like a fair. Okay. But that's basically caused by mechanical weathering processes. Okay. So you can imagine from this rock, okay, then you have the salt particles being disintegrated slowly over time. Okay. So that happens basically in thousands of years. No? Okay. So with respect to the transportation of weathering products, okay, so the products of weathering may stay in the same place, okay, which means that the disintegrated materials may stay on the same place or they may be moved to other places by ice, water, wind, and gravity. Okay. So the soils formed by the weathered products at their place of origin are what we call as residual soils. Okay, I mean like basically the residues of the rocks. Okay, so that's we call them residual soils. Okay, Now, an important characteristic of residual soil is degradation of the particle size. Okay? So, when we talk of residual soils, fine grain soil can be found at the surface, and then the grain size increases with depth. Okay, so you can probably have clays and seals on the surface, but as you go deeper in that residual soil profile, you can probably have sands or gravels. Then as you go deeper, you can have cobbles and boulders and so on and so forth. Okay, in such a way that at greater depths, angular rock fragments may also be found. Now, basically, residual soils is a bit problematic as well. No? When um, it is above the groundwater level, because they can also cause landslides. Okay, so you need to understand this type of source as well. Okay? In the masteral degree program, for example, when I teach unsaturated soil mechanics, I normally mention these problematic soils, such as these residual soils, the collapsible soils, and the expansive soils, because these are soils that a bit problematic above the groundwater level, which is under the realm of unsaturated soil mechanics. Okay, but we discussed that in the advanced degrees. For the moment, let's just focus on the soils below the groundwater level. Same as what Professor Das has focused on his book on geotechnical engineering, the principles of geotechnical engineering. This is now what we call as classical soil mechanics. So the things that I'm discussing to you now until the end of this course is now what you call as the classical soil mechanics. Okay, which means that in the derivation of the formulas later on, normally these are derived under saturated conditions, no? For example. Okay. Now, for the transported soils, they may be classified into several groups, depending on their mode of transportation and deposition. So, there's what you call as glacial soils, which are formed by the transportation and the deposition of glaciers. We don't seem to have that here in the Philippines. Okay. We have also alluvial soils, which are transported by running water and deposited along streams. Then you also have the lacustrine soils. These are formed by deposition in quiet lakes. Okay, sometimes lacustrine soils are also a bit problematic. Then you have marine soils formed by deposition in the seas. And then we also have aeolian soils, which are transported and deposited by wind, such as these loess soils. Okay. And then you also have colluvial soils formed by movement of soil from its original place by gravity, such as during landslides. Okay. So I think here in the Philippines, we all have these soil types, okay, um, except the glacial soils. No? Okay. Um, if you go to Canada, for example, they have their what we call as glacial till. Okay, glacial till has the same composition as residual soils. Okay, I- if you try to observe there in the Talamban campus, okay, just above the civil engineering department, okay, if I still recall it right, you have there a road going to the camp, the retreat house, no? Okay, the retreat house. Um, on the side there, on the side slope, I did some research there, no, where we installed some sensors. Um, that can measure or that can determine some parameters on the soils above the groundwater level. So there, we did some test pits. No? Okay, so you can imagine if you go up on that road on the left side, that slope there. I, I During my research, no, when I did my PhD research, I always go to that part of the slope to do some monitoring, no, of the sensors that I installed there together with my Japanese professor at the time. Okay? So there, the material is basically a residual soil. Okay, when we excavated, no? When we did some test pits, the material there can be described as a residual soil of the limestone rock. Okay, so the soils that you find there are basically residual soils of these limestone rock materials. No, the whitish, no? The yellowish or the whitish soil grains. Okay. Yeah. Okay. So far we have discussed igneous rocks. Okay. So let's talk a little bit about sedimentary rocks. Okay. So the deposits of gravel, sand, silt, and clay formed by weathering may become impacted by overburden pressure, and they can be cemented by agents like iron oxide, calcite, dolomite, and quartz. Okay. So cementing agents are generally carried in solution by groundwater, and so they fill the spaces between the particles, and they form sedimentary rocks. Okay, so rocks formed in this way are called detrital sedimentary rocks. Okay, so all detrital rocks have a clastic uh, texture, no? Which means composed of grain. When you say clastic, they're composed of grains, no? Grain materials. Okay, so I think um, there in Cebu there is a place. I think um, just around Pitos area. Pitos area. I have there what you call as Pulang Bato. No? Okay, Pulang Bato. Okay. So this Pulang Bato in English terms, they are basically what we call as the dolomitic rocks. No, okay, they are reddish in color. Okay, they are actually a weathering output of these limestone rocks. Okay, dolomites. These are dolomites. Okay, now the types of sedimentary rocks are formed depending on the particle size which they are being cemented, no? Okay, or being bonded together. For example, for granular or larger particle sizes, so say for grain sizes between 2 to 4 millimeters or larger, when these particle sizes are being cemented together, they become or they can now be called as conglomerate rocks. Okay, yeah. So if these sandy materials, okay, um, if they become cemented, okay, or being bonded together, then we call them as sandstone. Okay. Now, in the case of silts and clays, if they're bonded together or being cemented together, then they become mudstones or shales or clay stones or silt stones. Okay, so these are sedimentary rocks. Later on, we will have the grain size distribution as well. Okay? Uh, rock can also be formed by chemical processes. Okay, so rocks of this type are classified as chemical sedimentary rock. Okay? So these rocks can have a clastic or non-clastic texture. Okay. Now, these sedimentary rocks may undergo further weathering to form sediments, or maybe, okay, subjected to the process of metamorphism to become a metamorphic rock. Okay, so here we have other examples of sedimentary rocks such as limestone, rock salt, dolomites, and gypsum, for example. No? And these are the chemical compositions of these rocks. Okay. For example, this limestone here, it is composed of calcium carbonate. Okay. Okay. Now, calcium carbonate usually reacts with water. Okay. Um, so when this calcium carbonate reacts with water, it tends to dissolve in such a way that you start creating cavities, no? Within the limestone. Okay. Then just give it time. With the continuous flow of water, these cavities will become caves later on. No? Okay. So when you see caves, usually the rock material there is limestone. No? When you see caves. Okay. So even in my case, even if I have not seen the rock material and but you tell me that there are caves there, then I already know that it's a limestone rock. Okay. So the figure here on the right is an example of an SEM of a limestone. No? Okay, being magnified, being magnified. So this is what you see when you try to magnify the limestone. Okay. Okay. So talking a little bit about metamorphic rocks. Okay. So metamorphism is the process of changing the composition and texture, okay, of rocks without melting. Okay, without melting by heat and pressure. So during metamorphism, new minerals are formed and mineral grains are sheared to give a foliated texture to metamorphic rock. Okay, so this is where you see the foliations, no? Okay, in rocks. Okay, so normally when you have foliations, these are sometimes metamorphic rocks. Okay. Now, metamorphic rock generally contains large quantities of quartz and feldspar. Okay, so under extreme heat and pressure, okay, metamorphic rocks may melt. Okay, they may melt to form magma, and then the cycle is repeated back to igneous rocks and sedimentary rocks. Now, examples of metamorphic rocks are the gneiss, slate, the schist, phyllite, marble, and the quartzite. Okay. Um, I think in my experience, uh, yeah, so far we have seen this gneiss, the slate, and this quartzite. This quartzite. Yeah, we have seen this in the field. Okay. So now let's talk a little bit about a soil particle size. Okay. Um, but looking at the time, I think it's now around 7:10. Okay, around 7:10 in my watch. Okay, and have a short break for about 10 minutes. That's my voice. Okay, and maybe some of you would like to have a toilet break. Okay, so can we have a 10-minute break? Okay, so it's now about 7:10 here in my watch. So maybe we can come back. Okay, please come back at around 7:20. Okay, then let's continue with the lecture. Let me just rest my voice for a few minutes. Okay, okay, thank you, everyone. lattice. Okay? So the layers are held together by hydrogen bonding. No? Okay. Um, so collinite occurs as platelets. Okay. Each with a lateral dimension of 1,000 to 20,000 Armstrong, where 1 Armstrong is about zero point 0.1 nanometer. Okay? And a thickness of about 100 to 1,000 Armstrong. So the surface area of the collinite particles per unit mass is about 15 square meters per gram. Okay. Then so this surface area per unit mass is now what we define as a specific surface. Yeah, specific surface. Now, aside from collinite, we also have the elite, wherein the elite consists of a gibbsite sheet bonded to two silica sheets. So that's this one here. That's side sheet bonded to two silica sheets. So this one. Okay. One at the top and and another at the bottom. Okay. Now the elite layers are bonded by potassium ions. Okay. And then the negative charge to balance the potassium ions comes from the substitution of aluminum for some tetrahedral sheets. Now, Montmorillonite, which again, for me is the most problematic of these clay minerals, has a structure similar to that of Eli, where one gibbsite sheet is sandwiched between two silica sheets. Now, in Montmorillonite, there is isomorphous substitution of magnesium and iron for aluminum in the octahedral sheets. So potassium ions are not present as in Eli. In the case of Montmorillonite, and a large amount of water is attracted into the space between the layers of this Montmorillonite clay, no? Which makes it or which gives it this expansive nature, no? Of this Montmorillonite clay. So basically, when we have a clay sample, okay, normally I always think of whether it is a collinite clay or an elite clay or a Montmorillonite clay. Now, the moment the SEM test will tell us that we are having a Montmorillonite clay, then in practice or in construction, we start to worry. Okay, because it's not really that worrisome, but what makes it worrisome is the cost of ground improvement. Okay, so this is just an illustration of what I have mentioned earlier. Okay, so for the collinite clay here in letter A, okay, so that is it's composed of one gibbsite sheet and one silica sheet, no? And then they are being bonded together by hydrogen bonding. Okay. Now, in the case of Elite, this one here, you have a gibbsite sheet sandwiched between two silica sheets. Okay, and then they're being bonded by potassium ions. Okay. Okay. So the same case for montmorillonite, you also have gibbsite sheets bounded between two silica sheets. Okay, and then they are bonded together by these exchangeable cations. Okay. So what this figure is telling us is that again, when we talk of clay soils, the clay soils have a different soil structure than the other soil types because they are mainly composed of sheets. Okay? And that gives them a different behavior. That's why, for example, in terms of permeability, the flow of water in clays is very, very slow because of you can just imagine how the water will flow between the sheets. Okay, So it will have an erratic pattern. Huh? It cannot easily flow into the sheets. Huh? That's why the permeability in clays is very, very slow. Later on, we will have a topic on permeability. Okay, so here we just have an atomic structure of the kaolinite. Yeah. So here you have some oxygen, okay, hydrogen and silicon. Okay, that's the composition of this kaolinite. Okay. Okay, so this one here is a composition or atomic structure of an Eli, okay, where it's composed of some oxygen, okay, hydroxyl, aluminum, potassium, atomic structure of a Montmorillonite clay. Okay. Now, here we see some scanning electron micrograph photos of kaolinite as well as Montmorillonite. Okay, so you can see the differences, even though they are the same clay minerals, but they have different, okay, quite different. That's why in the field of practice, if we are in clay mineral we have, we can probably identify it through these um, results, no? Okay, from the SEM. Okay, now in clays, there is now what we call as a diffuse double layer. No? Okay, later on, if you want to do research in clays, for example, the specific on clays, you will have to deal with this diffuse double layer. Okay. So in dry clay, the negative charge is balanced between or by exchangeable cations like calcium, magnesium, sodium, and potassium surrounding the particles being held by electrostatic attraction. Okay, that's in a dry clay. Now, uh, that's this one here. Okay. Now, when water is added to clay, these cations and a few anions float around the clay particles. Okay. So this behavior or this configuration is now what we call or was referred now as the diffuse double layers, huh? Such as this one here, no? A diffuse double layer. Okay. So the cation concentration decreases with distance from the surface, okay, of the particle. Okay, so this one here. Okay, so the cation decreases from a distance from the particle. Okay. Now this diffuse double layer uh, shades the behavior also of clay from the other types, no? Such as sands and gravels, for example. Okay, that makes them or that makes them a cohesive material. Because in practice, there's what we call as cohesionless materials, and there's what we call as cohesive materials, no? With respect to the shear strength parameters. Okay, so the diffuse double layer usually contributes to the cohesiveness of um, the clay source. Okay. Now, since water plays an important role, no? It plays an important role in the behavior on the diffuse double layer for clays. Okay, so let's just talk a little bit about this character of the water. Okay, so water molecules are basically polar. Okay, now the hydrogen atoms in the water molecule are not asymmetric or that, sorry, axisymmetric um, around an oxygen atom. Instead, they occur at a bonded angle of 105 degrees. Okay. Um, as a result, a water molecule has a positive charge at one side, okay, and a negative charge at the other side. Okay. So which is now known as a dipole. Okay. So for example, here you have one oxygen and two hydrogen atoms. That's why it's called H2O. So dipolar water is attracted both by the negatively charged surface of the clay particles and by the cations in the diffuse double layer. Okay. So the cations in turn are attracted to the soil particles. Okay. So that's why clays and loams, for example, no clay loams, for example, they are a very good agricultural material for planting, for example, because they can hold water because of this behavior. Okay, yeah, they can hold water, which is good for the plants. Now, a mechanism by which water is attracted to clay particles is what we call as hydrogen bonding, where hydrogen atoms in the water molecules are shared with the oxygen atoms on the surface of the clay. Okay, yeah. So some partially hydrated cations in the are also attracted to the surface the clay particles. Now, these cations attract dipolar water molecules. Okay, so this one here, no, dipolar. So this is now a figure of that hydrogen bonding with dipolar water molecules. So again, this hydrogen bonding contributes to the ability of the clay materials to hold water. Okay, which is quite good for of attraction between water and clay decreases with distance from the surface of the particles. Okay? Now, all the water held to the clay particles by force of attraction is known as the double layer water. Okay? Now, the innermost layer of the double layer water, which is held very strongly by clay, is now what you call as the adsorb water, no? On the surface. No? This is on the surface. Now, air is more viscous, free water. Okay? Of water around the clay particles again gives clay soils their plastic. Okay, so that's why there's what we call as a low plastic clay and a high plastic clay, high plasticity clay. Um, Again, in practice, we really don't like these plastic clays, no? Because they are a bit problematic. We would prefer a low plastic clay, for example. Okay. Later on, we will be discussing that. So here just explains why we have the plastic properties of such. Now, the presence of clay minerals in a soil aggregate has a great influence on the engineering properties of the soil as a whole. Okay? When moisture is present, the engineering behavior of a soil will change greatly as the percentage of clay mineral content increases. Okay. Now, when the clay content is about 50% or more, the sand and will float in a clay matrix, and the clay minerals will now primarily dictate the engineering properties of the soil. In practice, no, okay. Normally, we try to assess if it is purely silt or if it is a sandy silt or if it is a clay silt. Okay, to the USCS classification. Because if it is a clay silt, then we treat it, no, as compared to a sandy silt. Okay, the geotechnical analysis or assessments will be treated differently, um, a clay silt as compared to a sandy silt. Okay, so this is what is meant by the change in the engineering behavior. Okay, especially when you do bearing capacity analysis, lateral earth pressure analysis, or slope stability. Okay, I think this is just an illustration of that A water. Okay, here this is a typical Mont Morillonite particle. Okay, wherein the gray color here is the double layer water. Okay, um, this is the Mont Morillonite. So with the double with the sorry with the Mont Morillonite crystals, um, just on the surface of it is you have the adsorbed water, okay, and then it's surrounded by the water. Now that's for a Mount Morillonite clay. So for a kaolinite clay, yeah, so this is now the kaolinite crystals, okay. So this is the adsorbed water, and then uh, out you have the double layer water. Now with their corresponding thicknesses in terms of Armstrong. Okay. In geotechnical engineering, a also use is specific gravity. It's the same definition of the specific gravity that you're also using in hydraulics, okay, or fluid mechanics. Okay? So specific gravity is defined as the ratio of the unit weight of a given material to the unit weight of water. Okay, only that here our materials are soils. Okay? So the specific gravity of soil solids is often needed for various calculations in soil mechanics, where it can be determined accurately in the laboratory. But in the absence of laboratory, you can have this table here as initial reference for the specific gravities for different of minerals. So that's why if you have a sandy material, for example, wherein you know that the dominant material, for example, then you would know specific gravity of that sandy material is around 2.65. Okay? And then that's the one you use in the calculations, for example. In practice, yeah, this is about the values that we normally use, about 2.6, 2.65. Uh, um, depending on the dominant mineral. Um, Later, when we do classifications, for example, when we do the unified soil classification systems, um, the properties that we need for the soil classification system is size distribution test or the grain size data. Okay. Now, this one can be derived analysis of the soil. Now, mechanical analysis is the determination, okay, of the size range of particles present is expressed as a percentage of the total dry weight. Okay. Now, there are two methods are generally used to find the particle size distribution of, okay, for particle sizes larger than 0.07 millimeters in diameter, then we normally do the sieve analysis. Okay? But for particle sizes smaller than 0.075 millimeters in diameter, we normally do hydrometer analysis. Okay. Although in practice, normally we just do the sieve analysis. Okay. But some are projects wherein we are forced to do hydrometer analysis because um, in the case of the USCS system, below the 0.075 millimeter, these are already considered as the fine content. But in the fine content, we know earlier that the fine content is composed of silts and clays. Okay, but there are some projects in we are forced to do ground improvement. Okay, but one this ground improvement technique that we are implementing has a strict qualification with respect to the clay content and the silt content. That means if the clay content will be higher than by this amount, okay, in that particular material, then such ground improvement technique will no longer work. Okay, so that's why we are forced to do hydrometer. I think the project somewhere near Laguna Lake. Yeah? Okay. We were building an industrial plant there. Okay. Okay. So sieve analysis consists of shaking the soil sample through a set of sieves that have progressively smaller openings. Okay. The smallest size sieve that should be used for this type of test is the US number 200 sieve. Okay. You can probably see this later on in your geotechnical laboratory. Now, hydrometer analysis is based on the principle of sedimentation of soil grains in water. Uh, when a s- when a soil specimen is dispersed in water, the particles would settle. Okay, they would settle at different velocities. Okay, so depending on the shape, the size, the weight, and the viscosity of water. And because of these different velocities, then you can then try to distinguish between silts and clays. Okay, so we have been mentioning about these sieve sizes. So here you have the typical sieve number, okay, and then the corresponding opening, which will determine the grain size diameter as well. Okay, so that means for a number for sieve, that's equivalent to 4.75, and then a number 10 sieve is equivalent to 2 millimeters, and then number 200 sieve is equivalent to 0.075 millimeters. Okay, and this is how we um, put them in the laboratory. Okay, we put them by stocks. Okay? I'm not sure if you have already started doing your geotechnical laboratory. Okay, so I think this is a bit better now. Okay, because during our time we still experience shaking the sieves manually. No? Okay, so I think by now it's already automatic. Okay. Now, in the conduct of sieve analysis, okay, one must first oven dry the soil, okay, and then break all lumps into small particles, okay. So this is what you do in the lab, okay. Then the soil then is shaken through a stack of sieves with openings of decreasing size from top to bottoms, okay. So the larger sizes on top, the smaller sizes at the bottom, okay. And then a pan is placed below the last stop. Okay. Now, after the soil is shaken, the mass of soil retained on each sieve is determined. Okay, so we measure, no? We measure each mass retained in each sieve. Okay, now portions retained on each sieve are collected separately and oven dried before the mass retained on each sieve is measured. Okay, so that means that if we try to do it step by step, so what we do in the sieve analysis is first, we determine the mass of soil retained on each sieve, that is M sub 1, M sub 2, until M sub n, depending on the number of sieves. Okay. And then if there are soils passing through the last sieve, then there is still some soils in the pan. Okay. Then we call that M sub p. Okay. And then we determine the total mass of the soil. Okay. Wherein the total mass of the soil is now M sub 1, M sub 2, until M sub I, until M sub n, which is the last stack, plus the mass of soil in the pan, no, at the bottom. Okay. That will be your total mass. Then we determine the cumulative mass of soil retained above each sieve. Okay. So for example, for the ith sieve, the cumulative mass will be M sub 1, M sub 2 until M sub I. Okay. So the mass of soil passing through the ith, no, the ith sieve, okay, or the nth sieve, okay, will now be the total mass, which is derived from here minus the sum of um, the masses until the ith sieve. Okay, this one here. Okay. So then the percent of soil passing the ith sieve, or we call it the percent finer, okay, F is now equal to this value now here in item 4 divided by the value in item 2 multiplied by 100. Okay. So this is now the general approach. Okay. So I think if you have already have the geotechnical laboratory, you will also be computing it like this. Now, once the percent finer for each sieve is calculated, okay, that's step 5, the calculations are plotted on semi-logarithmic graph paper with the percent finer as the ordinate, okay, arithmetic scale, this one, okay, arithmetic scale, opening size as the abscissa. So this one here in logarithmic scale. Okay. So this plot here is referred to as the particle size distribution curve. And yeah, it depends on how you place the values here. It can have this figure or it can have this figure. Okay. Mhm. In the case of Japan, for example, when I was still doing my doctoral research in Japan, normally the grain size distribution, we don't put it like this, but we put it in this direction. Okay. So it depends on your preference. Okay. So after the sieve analysis, we also have the hydrometer analysis. Okay. Wherein here it is assumed that all the soil particles are spheres. Okay. And that the velocity of the soil particles can be expressed by Stokes' law, just like this formula here. Okay. Yeah. Then we also have this formula here, D, where D is the diameter of the soil particles, okay, which is equal to K times the square root of L over T, okay, where K is a parameter equal to the square root of 30 U, okay, or this is nu, okay, where nu is the viscosity of water, okay, over the specific gravity minus 1, okay. Um, for this L, we will describe this in a while, okay. Now, combining these equations here, no, with Stokes' law, okay, uh, um, we now have these equations here. Okay, so we are just basically combining, um, Stokes' law, okay, with these formulas here. Okay, so then um, this where was that? Here, okay, this v here, okay, yeah, this v is the velocity, okay, which is the length over time, okay. So then we replace this one. Sorry, we replace this one here. Then you have this equation here, and then we take note that um, the density of soil is equal to the density of water times the specific gravity, because we know that the specific gravity is the density of the soil divided by the density of water. Okay. So if we substitute this one here, okay, so then you will get this one, this term here. Okay. And then, yeah, um, expressing these terms here with respect to these units. Okay. And so we can now have, yeah, this formula for the diameter of the particles, which is now equal to this formula here. Okay. So the 18 is now converted to 30, considering these units here. Okay. So that means if you want to follow this formula, then you have to be strict with um, the units of each term, okay, used in this uh, formula. Okay. 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 So going back in this formula, no, for the diameter of the soil particle in the hydrometer test. Okay. So this L here, because we know this one. This is the density of water. This is specific gravity. This one is that is the viscosity of water. Okay. And then this is time. But what is L? Okay. So L is basically this is the definition of L. Okay. Derived from the hydrometer equipments. Huh? Okay. So this is what you do for a hydrometer test. Okay, wherein this is now the water with the seals and clays being shaken up, and then you put there the hydrometer. Okay, so this hydrometer equipment, okay, the L in the formula is now basically the distance from the water level. Okay, so from this one here until the center of the hydrometer equipment. Okay. So that's the definition of your L. Okay. So here there are just some um, variations of the L in the hydrometer reading. Okay, so basically in the hydrometer test, what we can read is the hydrometer. Okay, the hydrometer reading, and that hydrometer reading will have a corresponding value of L. Okay. So then if you have that, then you can substitute it here. Then just measure the time. The rest here is basically constant. So it's just a function of L and time. Okay. Then you can determine this D for the diameter of the soil particles. Okay. So this is now an example of a particle size distribution curve with some results of the sieve analysis, which is this one here. Okay, this is the result of the sieve analysis, and then this one here is the result of the hydrometer analysis. Okay, so then we combine them. We combine the two results for the sieve analysis and the hydrometer analysis to have a complete picture of our particle size distribution curve. Okay, so again, in the USCS classification system, so until the sieve number 200 is still considered as sand using sieve analysis, but beyond that number 200 sieve, or that's after or lower than, smaller than 0.075 millimeters, you already have the silts and the clays um, determined by the hydrometer analysis. Okay. Okay. So there are some parameters that we can derive from the particle size distribution curve. Okay. So one is the effective size, which is a D10. Now this parameter is the diameter in the particle size distribution curve corresponding to 10% finer. Okay. So the effective size of a granular soil is a good measure to estimate the hydraulic conductivity and the drainage through the soil. Okay. For example, in I think the Hazen's formula, for example, in permeability, the Hazen's formula is using a parameter of D10, okay, which you can get from the particle size distribution curve. Okay. Now you can also calculate for the uniformity coefficient, okay, C sub u, wherein this is a parameter which is defined by D60 over D10, which you can also get from the soil particle size distribution curve. Okay? And then you can also have the coefficient of gradation, that's C sub C, which is defined as the square of D30 over D60 times D10. Okay. So how do we get these values from the grain size distribution curve? Okay. So for example, this one here, you have the plot of the grain size distribution curve. Okay. And then you have here the percent finer. So if you want, again, if you recall, this is the D10, D30, and D60. Okay. So if you want to get D60, for example, then D60 is somewhere here. Okay. Yeah. So that's the percent finer at 60%. Then you project it here. Then once it touches the curve, then you project down. Then that's the value for the D60. Okay, so this is now the particle size for your D60. So then, for example, if this um, percent finer at 60%, then it can probably have a value of zero point 0.5, for example. Okay, then you can substitute a zero point 0.5 here in these formulas. Okay. So again, for D30, so that's this one here. To project, then project it down. Then this is the value of D30. But then you just have to be, just to complete the scale here, so that you can easily find the value. And then for D10, that's this one here. Okay, so then probably this is probably the value for D10. Then these values in millimeters, you can substitute it here to get these parameters, which is also mentioned later on when we do the uh, soil classification, the unified soil classification system. Okay. Um, so after we have the grain size distribution curve, okay, we can also try to derive the percent gravel, the percent sand, as well as the percent silt and clay. Okay? So normally, the difference between um, the 70 between 76.2 millimeters and 4.75 millimeters, that's actually the percentage for gravel. Okay. Yeah. And then the difference between the 4.75 millimeters and 0.075 millimeters, that is treated as the percentage um, for sun. Okay. And then if yeah, if nothing is left, um, in the pan, for example. Okay. Yeah. So that's this difference now is the percentage for the silt and the clay. Okay. For example, where is this 76.2 millimeters? Okay. So yeah, it's not here in this graph. Okay. So if it's not here in the graph, so automatically there is no gravel. Okay, that's zero. Okay. So here, for example, the 4.75. Okay, so that's somewhere here. So that's probably 100%. Okay, so this is correct. Okay. And then the 0.075, maybe that's somewhere here. Okay. Okay. 0.075, then you project it up, then the value is about 62%. Okay, so this is okay. Yeah. Okay. So in this case, if we subtract another two, that's 100 minus 100. So that means, yeah, indeed, it's zero gravel. Then 100 minus 62, that means that's 38% sand. Okay, between this range. That's 4.75 minus 0.075. Okay, I think this is for the US soil classification system. Okay, this is the boundary. Then if there's nothing left, then we have about 62% of it is silt and clay. Okay, so depending which one is the majority material, if the majority is silt, okay, then this can probably be a sandy silt. Or if the majority is clay, then this can probably be a sandy clay, for example, in the USCS classification system. Okay. I think that will be our next topic. Okay. So this is only applicable if you want to know the percentage of gravel, sand, and then silt and clay. If you still want to break this down further, then you can do um, yeah, the hydrometer test, no? Okay, to simply break the percentages of the silt and clay. Okay, so now that we have the grain size distribution curve, then we just need to understand the different uh, types, no? Okay, of particle size distribution curves. Okay, so here we have three types. Okay, so curve one here, this one here, is now what you call a poorly graded soil, in which most of the soil grains in this poorly graded soil are the same. Okay, they're relatively the same. Now, curve two represents a soil in which the particle sizes are distributed over a wide range. No? Okay, so this one here. If I hope you're seeing my cursor, okay, this one here. This is a well-graded, okay, well-graded soil. Okay. So a well-graded soil has a uniformity coefficient greater than 4 for gravels and 6 for sands, and a coefficient of gradation between 1 and 3. So again, recall this is how we derive that. Okay. Um, and then a soil might have a combination of two or more uniformly graded fractions. Okay. Um, and then in the figure, this is what we call a curve tree. Okay. So this one here. Okay. So this type of soil is what you call a gap graded soil. If this is the shape of the grain size distribution curve. That means there are some grain sizes which are missing. Okay. So these are the three um, soil types with respect to the grain size distribution curve. It's either you have a well-graded soil, a poorly graded, or a gap graded. Normally in the case of, for example, in gravels. Okay. Now, I think this will be the last item, I believe. So, the shape of the particles present in a soil mass is equally as important as the particle size distribution because it has significant influence on the physical properties of a given soil, such as the maximum and the minimum void ratios, the shear strength parameters, and the compressibility, so on, so forth. Okay? Now, bulky particles are formed mostly by mechanical weathering of rock and minerals. Okay? Now, geologists, from their end, they sometimes use the terms angular, subangular, subrounded, and rounded to describe the shapes of bulky particles. Okay? Now, small sand particles located close to their origin are generally very angular. Okay? But when the sand particles are carried by wind and water for a long distance, then they can be now subangular to rounded in shape. Yeah? Okay. That's why in rivers you can see rounded pebbles. Okay, because that's already being um, yeah being refined, no? By the flowing water, for example. Okay. Now, flaky particles, very low sphericity, where particles are predominantly clay materials. Now, this is in the case of clay materials. Okay. Um, Needle-shaped particles are much less common than the other two particles, such as in coral deposits. No? That's why when we have coral deposits, we really have to be careful because of their needle-shaped particles. No? Okay. So that means when we have sandy soils or gravels, normally they are bulky particles, but in the case of clay minerals, they are somewhat flaky particles because they are composed of sheets. Okay, so just an illustration of that. Okay, so this is what we mean by angular, subangular, subrounded, and rounded particles. And then in actual, this is how we see them. Okay, so this is angular, subangular, okay, subrounded, and you have the rounded. Okay, this we usually like to play around. Okay, so just a summary. I think uh, rocks can be classified into three basic categories: the igneous, the sedimentary, and metamorphic rocks. Okay, and then soils are formed by chemical and mechanical weathering rocks. Okay, and then based on the size of the particles, soils can be classified as gravel, sand, silt, and clay. Okay. And then according to the USCS system, which is now universally accepted by geotechnical engineers all over the world, okay, the grain size limits of gravel, sand, and fines, which are the silts and clays, are as follows. Okay, so from 76.2 millimeters to 4.75 are gravels. Sands are 4.75 to 0.075 millimeters. Then the fines, which are the silts and clays, are less than 0.075, according to the USCS system. Now, clays are flake-shaped microscopic and submicroscopic particles of mica, clay minerals, and other minerals. And then clay particles carry a net negative charge on their surfaces. And then when water is added, a diffuse double layer of water is developed around the clay particles that is responsible for providing plasticity to clay soils. Okay, that's why there's what we call as the low plasticity clay and the high plasticity clay, for example. And we are usually worried with the high plastic waste in practice. Okay. So mechanical analysis, okay, is a process of determining the size range of particles present in soil mass. It consists of two parts, the sieve analysis for particles greater than 0.075 and the hydrometer analysis for particles less than 0.075. And this is now the general formula for the case of the sieve analysis. Okay? Now, in the hydrometer analysis, the percent finer than a given particle size d can be determined using the hydrometer reading L and the parameter K. Okay. Yeah. So just an example, which I just took from the book. Okay. Although anyway, my colleagues here will just of this through your seat work, maybe this Thursday. Okay. Um, so I'll just be giving one example because we don't have much time. Okay. So here in this example, the following are the results of a sieve analysis. Okay. So we have here the number 4 sieve, number 10, number 20, number 40, number 60, 100, 200, and pan. Okay. And then here in the lab, okay, so you measure the mass of soil retained on each sieve, okay, such as in grams. Okay, so here, for example, in this pan, there's no soil left. That's zero. And then the others, you were able to get the soil mass, no? Okay, with these corresponding values. So we are asked in this data to perform the necessary calculations and plot a grain size distribution curve. Determine the D10, D30, and D60 from the grain size distribution curve. And then calculate the uniformity coefficient C sub U, and then calculate the coefficient of gradation C sub C. Okay. Okay. So this is a sample calculation of that, which you will also do in the lab. Okay. So after we have the mass retained in each sieve, so we put it here. And then on the second column, we just put the opening sizes. Okay, so we know in the chart earlier that the number 4 sieve is equivalent to this diameter, the 4.5 millimeter, 4.75 millimeter diameter, and so on and so forth here. Yeah. And then from on the fourth column, we try to get the cumulative mass retained above each sieve. So you just simply add this value. So that's from 0 to 21.6, that's this value. 21.6 plus this value is 71.1, and so on and so forth. Okay. Then you get the total here. That's about 450. Okay. Then you can now get the percent of finer. Okay. Which is now for example, to get this value, that's the the total mass, okay, the total mass, okay, um, minus the value at column 4, this one here, okay, times 100, and that will give you the percent final. For example, this value of 100, that's 450 over 450 minus column 4, but column 4 for this sieve is 0. So that means that's 450 over 450 times 100 is equivalent to 100%. And then you do the same process for the rest, then you can get these values. Okay? So for the particle size distribution curve, we plot the percent finer against the um, uh, opening, no? Okay, or the soil particle diameter or the sieve opening. So then we can now plot it here. Okay. Yeah. And then once you now have the grain size distribution curve. You can just simply plot D60, D30, okay, then project it here. Okay, so for example, D60, I project it here, that's about 0.41 millimeters. Okay. D30, if I project it here, that's about, yeah, this one here, 0.185 millimeters. And then D10, that's somewhere here. We plot it here, that's about point zero 0.01 or 0.09 millimeters. Okay. Uh, okay. 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 So if we continue, okay, so we can now calculate once we have this D60, D30, and D10. Okay, we can now compute the uniformity coefficient and the coefficient of gradation by just simply substituting those values here for D60 and D10 as well as D30. Okay, then we can get the values for C sub U and C sub C, no? For the uniformity coefficient and the coefficient of gradation. Okay. So I guess it's almost time. It's about 8:30. So I think this is just an example that I can give. I think my fellow teachers here can probably give you some more examples. Okay. During Thursdays, they can probably give you some more seat works. Okay. There are many problems in the book. They can probably discuss that with you. Okay. Now, I think there's a question here if the presentation will be posted in the Canvas, I think. Okay. Now, again, all of these things, I just derived it from your reference book. Everything can be found in your reference book. So I would strongly suggest that you have a copy of the Principles of Geotechnical Engineering by Das. Okay, try to read such book. Then you will find out that everything that I have discussed, I just found there. Okay, so the reason for me doing that is I don't want you to worry about the slides. Okay, what is more important is you try to read the book. Okay, so I'm actually slowly training you to try to read because later on, if you want to proceed to a master's degree or a PhD degree, you will be learning things, you will be slowly learning things by yourselves. So that means in a PhD work, okay, for us, if you are called a PhD student, then you must be able to open a book, try to read a book, and try to understand it by yourself. Okay. So only that in the undergrad, what I am doing is I'm just trying to discuss some items of the book, but basically the better learning is for you to read the book by yourself. Okay. And if you have some questions, you can always ask me or my co-faculties here. You can always ask us if you have some questions or clarifications. And the moment you ask questions, that's the time when I can see that you are learning. Okay. So I hope I have answered the concern in the chat. Um, Apologies. I will not be giving my slides, but I would strongly encourage you to read the book. Okay. Yeah. So try to have the book, try to read. You will learn some more there. Okay. Okay. The book is entitled Principles of Geotechnical Engineering, yeah, by Braha Das. Okay. Yeah. I think there is an electronic copy of this one also. Um, 1985 is quite old, I think. Um, I think there are already versions of 2000. I think the latest version is around 2018. 18. Yeah, that's the latest version. Okay, but of course you can use the previous versions. Okay, 1985 is too old. although the basic concepts basically are the same. Yeah, they're the same, but only that in the latest edition, there are already many editions of this book. I think it's already in the eighth edition. Okay, it's in the eighth edition. I think what I'm using is mm, the 2018 version. Okay, 2018. Yeah. Okay. Are there any more questions or clarifications? If you're shy to ask, you can just chat, and I will try to answer. Okay, you're welcome. Any more questions or clarifications? Okay. If there are no more questions or clarifications, maybe we can already adjourn. Okay. Okay. So if there's none, okay. So thank you very much, everyone, and have a nice evening. Thank you. Thank you for your time.
Thank you, sir.
Goodbye, sir. Thank you.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
Bye. Thank you.